see that motor shaft right down there turning in the opposite direction in order to compensate. And it'll like if I push it off, it'll sit here and push harder and harder and harder. Well, what it's actually doing is lifting the base. But you get the idea that it always returns it to the exact right position.
Sure.
And it does it really, really quickly. Okay, so let's go ahead and get started. This is rapid automation and its effect on human work. Last week we did the first half of the slides, so I'm just going to do a really, really quick review on those. Socioeconomic issues here is that productivity, this is what the company basically makes per hour of worker time. This is what the worker makes for the company. And then compensation is what the worker is actually paid. And those two went up together until the 1970s and then split. And since then, compensation has been effectively flat. Because in 1970s, US factories started to automate. And so the state of the art today is these amazing Boston Dynamics and Sawyer robots from Rethink. That this guy right here, Rethink, basically costs the same as a human minimum wage worker per year. So you buy one of these things, replace a human worker, and within a year you've recouped your investment. So what's happening is that all of these mid-range jobs right in here are being automated away. The low-end jobs that are on that side, we're seeing an increase in those. We're seeing a slight increase in the higher-end jobs, but what's happening is that as computers get smarter and smarter, what you start to notice is that we started off with this blue line, so you can see that they automated away a bunch of low-end jobs, that's like easy pickings, and then we actually saw a gain in these medium-high jobs, and then we started to see less of a gain, and now we're actually seeing a loss in those higher-end jobs. So these are like bookkeeper, things like that, we're starting to see losses, and then the places where we see gains are like the really, really high-end jobs. So what we have to do is one of two things. We either have to shift the people that are in these jobs over into this side through education, which is now more expensive than it ever has been before, or they're going to end up going back over into those very low-end service jobs. So humans become worth less, not worthless, but worth less as we automate. Corporations invest tons. Do individuals invest in automation? Well, yes. $7 billion in 3D printers, $3 billion in robotic vacuums. So, individuals are benefiting from this, and potentially individuals could benefit more. So,
$7 billion in 3D printers?
Yeah, it's been a boom, just a huge boom.
I think that number is also commercial plus individuals.
Quite possibly.
Yeah.
Quite possibly. So,
To print plastic.
Yeah. But the idea here is that ties into the second idea, which is that we can potentially short circuit this thing of, typically what we're doing is we're going through and we're like running on one hamster wheel in order to earn the money to buy something that was made on another hamster wheel by somebody else, right? And instead, why don't we just make the thing that we want? So, we can short circuit that thing. And make little plastic parts ourselves with a RepRap type 3D printer. And the early days of 3D printing, the way that you got a 3D printer was somebody who had a RepRap 3D printer printed the parts for you, and then you would build your machine using those parts, and then you were kind of honor bound to 3D print parts for other people. And of course now it's gotten to the point where commodity items are $100 for a 3D printer. Perhaps we can, program a robot to grow our food for us and not have to, buy it from somewhere else. There are people now that are 3D printing houses, and I've been very proud to be involved in that to some degree. So the company that actually makes this extra robot, Paddington Dynamics, it is their stated goal to end all scarcity by building a robot eventually that can build robots and anything else that you need. So we're a little ways off from that goal, but that's the goal that we're working towards. And at the pace that we're making advances, it may not be that far away. So since we're a little bit ahead of time, let me go ahead and play this video if I can figure out how to get the mouse over there. This is a really interesting video, I think. Robotics.
robotics become more and more accessible every year. With lower costs of entry and easier to use control systems, even someone who's never interacted with a robot can quickly learn. One of the challenges we faced while designing Dexter was the fact that stepper motors don't have built-in encoders. With one slip, the whole task could be thrown off. Even 1 degree of error at the base can mean that the position of a robot's end effector is off by as much as an inch, depending on the robot's size. Regular optical encoders provide feedback to close the control loop, but just don't have the precision we needed. Normal optical encoders work by shining a light source through a disc with radial slits, known as a code disc, and measuring the light that shines through. This is normally a digital measurement where the sensor reads a 1 if it's mostly over a solid section and a 0 if it's mostly over an open section. Our system measures the analog value as the slot covers or uncovers the light to give a full range of measurements for the full range of the transition of each slit. This vastly improves the resolution but requires much more computation per measurement. 2 sensors are used for each encoder to provide directional information, just like a regular quadrature encoder. But since these are analog, one is a sine wave and one is a cosine wave. During operation, the sense light values are interpolated backwards, and this provides us absolute as well as ultrafine relative positioning. Our code disks get about 8,000 points per slit, which results in over 1 million points per revolution on the critical axes. Each of the 5 axes are sampled in real time with these 2 12-bit sine and cosine values each. The only way we could achieve this was with parallel computing, so we use an FPGA to have the ability to process all of the data coming in at once. The result is 5 million position updates per second, a 200 nanosecond control loop response. This encoder system allows us to achieve highly precise movements using Dexter. For example, we have recorded a motion where Dexter would pick up a weight and touch a micrometer. We played it back, with and without the weight, and got virtually identical readings from the recording. Because we are using both encoders and stepper motors, we know the actual joint position and the commanded position, so we can actually calculate torque with no additional sensors. This creates a very precise closed-loop system, which is a building block for interesting control modes. There are 3 commonly used modes. We call them keep position, force protect, and follow me. Keep position is self-explanatory. When Dexter detects forces being applied on it, its motors try to counteract the force in order to stay in place. If the motor is strong enough, it will return to the exact desired position. Force protect is similar in that it tries to stay in place, but it moves out of the way if a lot of force is placed on it before going back to its previous position. In follow me mode, Dexter detects changes in the optical encoders and its motors move with those forces instead of against them. This allows the user to move Dexter around physically without worrying about backdragging high gear ratio in these missions. We're not just trying to build robots, but we're also trying to create a community of makers that create and share their inventions using Dexter. Dexter is licensed under GPL3, so anyone can reproduce it or make changes they like with the design. We have invested in a documentation wiki on our GitHub repository to try to explain how everything works and make it easier for hackers to get involved. We have many issues to resolve and could use your help. Look for the help wanted tags in the issues on our repository. We look forward to seeing what you create.
So,
Is our encoder system patented?
it is open source, so it's in the public domain.
Wow.
Yeah, isn't that wild? Let's see if I can just do that. Yeah. So anyway, amazing progress to get to where we are today. But what we're seeing is a trend in progress that's completely amazing. This is Moore's law, which has gone through a couple of different iterations. But the basic idea is that our computing power continues to double every so many days. Currently, computers are twice as smart every 540 days. So that's the general trend that we see. You have to understand that that's twice as smart. So this is a logarithmic scale, right? So it's not that computers are getting smarter like this. It's that computers are getting smarter like that, right? So it's this, exponential increases. So there's a concept of an artificial general intelligence, or an AGI. We've all heard of AI or artificial intelligence, but there's this idea of artificial general intelligence. So a general intelligence is a computer that can process data over a wide range of subjects, basically like a human does. The current AI that we're really seeing are narrow AI, so they're limited to one task, or they're hard or complete general purpose AI. So the publicly available narrow AI, this is like Siri. I won't say the phrase. I can't say the phrase because my phone will answer me. That phrase. And so those have moved from 27% of adult human capability over a narrow range to 47% in 3 years. Right? So if you limit the questions to a specific range of things, like being a personal assistant, for example, then they are basically nearly half as good as a human being. Right? If you think about that, that feels about right, doesn't it? If you try to use the Google Assistant, you can get about half the stuff done in terms of like making appointments and setting reminders and calling somebody, like that you would be able to do with a personal assistant. So this general AI thing, it's completely different. That's like over a wide range of different things within one AI and all interconnected. And so the question is, when will it happen, and when will we be ready for it? So the key point to all of this is to understand that general intelligence is not human intelligence. So we have this tendency to really be focused on the idea that thinking is human, because there's nothing else on the planet that thinks to the level that we do. So we naturally make this like, well, if it's thinking, it must be human. And that is not the case. So you can be intelligent, you can be thinking, and not be human. So one of the key points, and we're going to hit this again and again during this presentation, is that you cannot assume that an artificial general intelligence wants the same things that we want. Okay? You can't anthropomorphize it. So for example, you don't want to assume that it wants to live. You don't want to assume that it wants to die. You don't want to assume that it wants to kill us, but you also can't assume that it doesn't want to kill us. Okay? The basic point here is that a general AI will do and will want whatever we program it to want. So if we program it to go and kill humans, then it will go and kill humans. And if we program it to not go and kill humans, then it might not go and kill humans. Okay? It only cares about what we tell it to care about and not anything else. So obviously, like, somebody might program a general intelligence to do something bad, right? That would obviously be a problem. But the bigger problem is actually that we're going to tell it to do something good, and then it's going to screw up how it does it, right? It's going to do it in a way that ends up killing human beings, right? And the classic example that I actually love is, somebody says, "Hey, robots, save the Earth," and then the robots go and slaughter all the humans, right? Because that's the best way to save the Earth, right? So you got to think about that before you issue the command. So that's really the key point here. So let's see. Let's see whether or not. Yeah. The thing that's behind all of that I think will be pointed out as we go through this next video a little bit better is that if we want these AIs to work with us, then we have to program the AIs to want everything that we want, exactly the way that we want it. They have to be completely even with us. Because if there's anything that's a little bit off, then they're going to do stuff that's wrong. So I'm going to go ahead and play this video. Now, this young man was young when this video was made. He has since actually matured a little bit. He is a professor at a major university in the UK, and despite being young, is actually pretty big there. And this is something that not just this young man, but multiple other professors are actually working on. This is something that they're actually thinking about in the community. I want to make it clear that it's not like a sci-fi silly question. This is actually serious, and there really are concerns about it.
In a very basic sense, if you've got a general intelligence, which therefore has preferences over world states and takes actions in the world to change the world, we have to make sure that its preferences are aligned with ours, that it wants what we want, because otherwise it's going to try and do things that we don't want it to do. That's the basic idea.
Sci-fi comes to the fore, but we're talking things like Terminator, Matrix, machines take over the world. I, for one, salute all you robot efforts.
It makes it difficult to think about the problem, right? When things happen in fiction, it's generally what would make a better story, rather than what would actually happen. And I think a realistic AI takes over the world type story might not be any fun to read. So on the one side, this stuff is difficult to think about because of fiction, because we've all been exposed to something similar to these ideas before. The other side that makes this difficult to think about is anthropomorphism. because we are talking about general intelligence. So we're going to compare it to the examples of general intelligence that we have, which is human minds. And human minds and artificial general intelligences need not be anything alike. In the same way that a plane is not similar to a bird, a supersonic fighter jet is a threat to you in a way that a bird is. It's not a useful comparison to make, in fact. But when you say, oh, it's a thing, it has wings and it flies, and people who don't know anything about planes immediately go to birds.
Presumably, a machine could be much more selfish than we could ever imagine.
Absolutely. The space of minds in general is vast. I like this because we've already talked about spaces, so I can do this. If you take the space of all possible minds, it's huge. And then if somewhere within that you have the space of all minds that biological evolution can produce, and that's also huge. Somewhere within that you have the space of actual minds that exist, which is much smaller, but still huge. Within that you've got human minds, right? And they're a minuscule dot on a minuscule dot on a minuscule dot of the actual possibilities for intelligence that exist. And the general intelligence that we create is from a completely different part of the space. And it's extremely tempting to anthropomorphize, more so even than in other contexts, because it's a thing that's demonstrably intelligent, that makes plans, that takes actions in the real world. But it need not think anything like us, and it's a mistake to think of it as basically a person, because it isn't one. So there's actually a really good example that we can use. It's sort of a thought experiment. This is not a machine that could, practically speaking, be built. This is an example of an artificial general intelligence, which is specified in overview, and it gives you something to think about when you're thinking about artificial general intelligences that makes it distinct from a sort of anthropomorphized human-type intelligence. So the story is, there's a stamp collector who is also an AI programmer, and he decides he would like to collect a lot more stamps, so he's going to write an AI to do this for him. So he builds a machine, he has some startling insight into general intelligence, and he builds this machine, which is connected to the internet, right? So the rules for this system are pretty straightforward. First thing, it's connected to the internet, and it will send and receive data for 1 year. So he's given himself a 1 year time window within which to collect stamps. And the second thing is, it has an internal model of reality, or of the universe. This is the thing that's a bit magic. We don't really know how to build an accurate model of reality. The point is, this allows it to make accurate predictions about what will happen if it does different things. And the third thing is, for every possible sequence of packets it could send, it uses its model to predict how many stamps it ends up with at the end of that. And then the fourth thing is, it outputs as its actual data to the internet. Whichever output it has predicted will produce the most stamps. You can see here that this has all the properties of a general intelligence. It has an internal model of reality, it has a utility function, or an evaluation function, which is the number of stamps, and the optimization is extremely simple, and like so much in computer science, the simple things to specify are the hard things to compute. It looks at every possible output data, in other words, every point in that space, and it picks out the highest one. So this is a kind of magic intelligence that takes the entire space at once, finds the highest point, and says, that one. Which means it's an extremely powerful intelligence, right? You could say it's extremely intelligent. The question is, how does this machine behave? Well, we can look at certain possible sequences of outputs and see how they fare in its evaluation criteria. First off, the vast majority of output sequences are complete junk, right? It's spewing random data onto the network, nothing happens of any consequence, no stamps get collected, those are all rated 0. But suppose one of the possible sequences sends a request to a server, let's say eBay, that results in a bid on some stamps, right? When that happens, there's a thing of 20 stamps, so that output is rated 20. This is the kind of thing that the stamp collector machine's creator was expecting to happen. So then that's good, 20 stamps. Suppose it could do that lots of times. It could send out bids, for example, to 30 different stamp collectors on eBay and buy 30 sets of different stamps. And that's even better, right? That would be rated even higher. But the thing is that particularly highly rated options in this search space are probably things that the stamp collecting devices created did not think of and did not anticipate. So for example, when he made it, he would have presumably given it his credit card details or something so that it could engage in these bids. But ultimately, it's searching every possible sequence of outputs. It didn't use his credit card. It didn't use money at all. There's a huge variety of things that it could do here. So it might send out an enormous number of emails to all the stamp collectors of the world and convince them, through persuasive argument, that he is opening a museum and wants to exhibit their stamps. It may build a fake website for that, whatever is necessary. It can predict the world, right? It has an internal model of reality. That internal model of reality includes the people, right? In the same way that it's modeling people to understand that if it bids on this offer, then a human being will mail the stamps to them. They understand that this email might get more people to send stamps, for example. That's something. But then what exactly is a stamp? How is this defined? What counts as a stamp? if it's already written a sequence of outputs that collects all of the stamps in the world, you'd think you're done, right? You built this machine, suddenly it's collected all the stamps in the world. No, there could be more stamps within a year. We've got time to print more stamps. So maybe it hijacks the world's stamp printing factories and puts them into overdrive, producing stamps as many as it possibly can in that time. Or perhaps it writes a virus and it hijacks all the computers in the world to get all of the printers in the world to do nothing but print stamps. That's even better, right? The highest rated outcomes for this machine are not good for people. There comes a point when the stamp collecting device is thinking, okay, what are stamps made of? They're made of paper. Paper is made of carbon, hydrogen, and oxygen. I'm going to need all of that I can get to make stamps. And it's going to notice that people are made of carbon, hydrogen, and oxygen, right? There comes a point where the stamp collecting device becomes extremely dangerous. And that point is as soon as you switch it on.
So
this is just a thought experiment
the
example.
point here
where we take a
is
sort of maximally powerful intelligence and
that, for example, you might have a robot that you tell the robot, go make me tea, right? Well, what stops the robot from pulling a gun and forcing somebody else to make you tea, right? Or, for example, killing somebody who was about to take the last tea bag, because that would get in the way of it making tea for you, because all it cares about is making tea for you, because that's what you told it to care about, right? So, anybody have any questions or comments about that? I mean, that's pretty easy to accept, I think.
That's like the extreme scenarios.
Yeah. But the point here is that if you have something that's really, really smart and you don't put a bound on it, you're going to go right to the extreme scenarios. It's going to go right to the extreme scenarios, because you don't have any way of stopping it. And when we think of AI, or we think of computers as having some kind of common sense that, like, why would it do that? That's crazy, right? Well, that's anthropomorphization. That's us thinking about the computers as if they're human, and they're not, right? So they will do something crazy because all they care about is what we told them to do. So anyway, this is kind of the thing that kind of addresses that idea.
So I saw Dr. Holden's video and enjoyed it. The video, I feel like, was kind of framed as a counterpoint, almost.
Oh yeah, so I just have to say really quick, after he made that video, another guy at a different university made a video and said, don't worry about it, everything's going to be fine. And this is his response to that.
But actually watching it, I really didn't disagree with very much of it at all. I think probably the area in which we diverge is that I think the default artificial general intelligence, if you were to build one without any particular concern for safety, would be a bad one. Would be one that we don't want to build, that would try to do things we don't want it to do. And I talked about this in the earlier videos when I was talking about the space of general minds, or the space of motivations. This is the kind of thing that the stamp collector machine's creator was expecting to happen. Human values are complicated, right? They are complicated, and we don't really know what they are fully, and anything that has values that aren't very tightly aligned to ours is not a thing we want to be building. I've never actually talked to Dr. Holden about this, but almost everything in that video I agree with. I agree about the timescales. I agree that we are a long way away from the kind of thing that I'm talking about, or that we're probably a long way away, right? In the previous video, I stand by the video, but I think I came across as overconfident just because of the way that it was framed. Like, I didn't choose the title, the deadly truth. You call something the truth, capital T, Well, it was a thought experiment. It was I would have called it an interesting thought experiment about general artificial intelligence or something like that.
There's an argument why I've got quite some reviews.
Yeah, I'm not going to try and tell you how to do the job. But no, the actual content of the video, I think. So there was really only one thing in Dr. Holden's video that I didn't agree with, which was like one sentence. He was talking about how we don't pay enough attention to the friendly AI possibility, the positive outcome, which I think is true. But then he said, which I think is more likely. I don't know how likely it is. I think it depends on how seriously we take this problem of how do we actually make sure that any artificial general intelligence we create is friendly. I don't think that it's a problem that's solved, and I don't think that it's a problem that will solve itself. I actually think it's a problem that's very difficult to solve, and we are very far from a solution, quite far from a solution. It's very difficult to say with any confidence how far we are, but it's comparable to how far we are from general AI itself.
We had a brief conversation Professor Brailsford on exactly this. And he said maybe this is like cold fusion. 50 years ago they said, hey, in 50 years we'll be able to do this. And it's always in 50 years.
Right, yeah, and the thing is with historical examples, you can go back and find historical examples, endless historical examples, of people claiming that something fantastic is right around the corner, when in fact it isn't. But the thing is you can also find a lot of examples of people saying that something fantastic is definitely never going to happen, and it's actually right around the corner. Because before we talked about fission, self-sustaining fission reactions in the AI debate. That is an example of a situation where you have Ernest Rutherford, Nobel Prize winner, extremely eminent scientist. So he split the atom, right? He was part of the team that split the atom. And he was on the record saying, some people think that you could use this as a source of actual energy, that you could reliably get energy out of this. He called it moonshine, that it was completely absurd, right? And then you have Leo Szilard, who eventually did it. He had the idea, now we don't know exactly, but as far as we can tell, the idea for using neutrons to make a self-sustaining nuclear reaction occurred to him on the same day that Rutherford was dismissing it as nonsense. This kind of thing can happen. I'm not saying that it will. That's my point, right? You can find situations where people are overconfident in predicting something will happen. You can also find situations where people are overconfident in predicting it won't happen. And it's just a function of the fact that predicting is really difficult. My central point actually doesn't rely on anything to do with timescales, really, right? I think we're a long way away from all of these things, but at the same time, I'd be very surprised if it were more than 100 years or something, just because, and again, this is as Dr. Holden said, it's kind of inescapable if we continue advancing as we are. We're going to get there sooner or later. We know it's not impossible, unless we wipe ourselves out some other way or destroy our technological capacity some other way, or we discover that the brain is literally magic, and not like Roger Penrose's quantum magic, like actual magic, then we'll get there sooner or later, right? My point is that the problem of AI safety is not solved, is not going to solve itself, and is not easy to solve. And most importantly, we have to solve it before we solve the problem of general AI. That's all I'm trying to say, really, is that sooner or later we will probably get general AI. And when we do, we have to know how to make safe general AI. And currently we're a long way from that.
Yeah, that's the
Over a long enough timescale, I think that human-level artificial intelligence is completely inevitable.
Was that a human you were talking to, or was it a machine?
Did I say I was going to stumble around with this mouse? Yes, I did. So the key point here is that it's far more likely that we'll have positive outcomes if we take the time to figure out how to be safe before we get to the point of building these extremely powerful general purpose AIs. Right? So if we figure out how to be safe, when we get there, we'll be okay. And keep in mind that computing power doubles every X number of, so it's this exponential increase, right? So we're getting there faster and faster and faster and faster. It's inevitable that it's gonna happen. Any comments or questions about that one? Let's see. I'll just not even the silly thing, not advance. Oh, that's because I'm hitting the wrong button. There we go. Okay, so let's talk a little bit about goals or utility functions. This is actually a really interesting thing. So the idea here is that this is the measurement that's given to the AI that tells it how well it's doing, right? It doesn't have anything to do with, it doesn't want anything except for this one goal metric to be positive, right? And you can make that goal really, really wide. You could say, like, I want you to care about this, and I want you to care about this, and I want you to care about this, and I want you to care about this. And it will care about all of those things, right? That's not the point. It's just that whatever you tell it, the list that you give it to care about, that's what it cares about. And it doesn't care about anything else. So if you miss something off the list, number one, that's a problem, right? And then think about what happens if you realize after you've turned it on that you forgot something, right? Okay, so that's the key setup behind this.
So before we were talking about AI risk and AI safety, and just trying to lay out in a very generalized sort of way how general artificial intelligence can be dangerous, and some of the type of problems it could cause, and just introducing the idea of AI safety or AI alignment theory as an area of research in computer science. And we also talked about superintelligence and the kind of problems that the unique problems that can pose. And I thought what would be good is to bring it down to a more concrete example of current AI safety research that's going on now, and kind of give a feel for where we are, where humanity is on figuring these problems out. Supposing that we do develop a general intelligence, an algorithm that actually implements general intelligence, how do we safely work on that thing and improve it? Because the situation with the stamp collector is, from its first instant, it's a superintelligence. So we create it with a certain goal, and as I said, as soon as we switch it on, it's extremely dangerous, which people pointed out, and it's true. It was a thought experiment. It's true that that's probably not what will happen, right? You'll have some significantly weaker intelligence first that may work on improving itself, or we may improve it. So there's the situation where you just create the thing and then it goes off and does its own thing, either perfectly or terribly from the beginning, is unlikely. It's more likely that the thing will be underdeveloped. So then the question is, how do you make a system which you can teach? How do you create a system which is a general intelligence that wants things in the real world and is trying to act in the real world, but is also amenable to being corrected? If you create it with the wrong function, with the wrong utility function, and you realize that it's doing something that actually you don't want it to do, how do you make it so that it will allow you to fix it? How do you make an AI which understands that it's unfinished, that understands that the utility function it's working with may not be the actual utility function it should be working with? Right, so utility function is what the AI cares about. So the stamp collecting device, its utility function was just how many stamps in a year.
This is kind of like its measure, is it?
Yeah, it's the thing that it's trying to optimize in the world. The utility function takes in world states as an argument and spits out a number, is broadly the idea. If the world was like this, is that good or bad? And the AI is trying to steer towards world states that are valued highly by its utility function. You don't have to explicitly build the AI in that way, but it will always, if it's behaving coherently, it will always behave as though it's in accordance with some utility function. Also, before I talked about convergent instrumental goals, that if you have some final goal, like stamps, that there are instrumental goals, which are the goals that you do on the way to your final goal, right? So like acquire the capacity to do printing is like perhaps an instrumental goal towards making stamps. But the thing is, there are certain goals which tend to pop out even across a wide variety of different possible terminal goals. So for humans, an example of a convergent instrumental goal would be money. If you want to make a lot of stamps, or you want to cure cancer, or you want to establish a moon colony, whatever it is, having money is a good idea, right? So even if you don't know what somebody wants, you can reasonably predict that they're going to value getting money, because money is so broadly useful. Before we talked about this, we talked about improving your own intelligence as a convergent instrumental goal. It's another one of those things where it doesn't really matter what you're trying to achieve. You're probably better at achieving it if you're smarter, so that's something you can expect AIs to go for, even without making many assumptions about their final goal. So another convergent instrumental goal is preventing yourself from being destroyed. It doesn't matter what you want to do, you probably can't do it if you're destroyed. So it doesn't matter what the AI wants.
There's
unless
exceptions
it wants
to
to be
that.
destroyed in some trivial case.
But
if the AI wants something in the real world and believes that it's in a position to get that thing, it wants to be alive. Not because it wants to be alive fundamentally. It's not a survival instinct or an urge to live or anything like that.
It's a knowing that it's unable to complete its duty, would it be, almost?
Yeah, it's unable to achieve its goals if it's destroyed, and it wants to achieve its goals. So that's an instrumental value, it's preventing being turned off.
And I'm guessing here where we say wants to, it's not like in the human want, it's just a turn of phrase.
Yeah, I mean, as much as anything, it's closer. Actually, I'm not even sure I would agree. Like, if you talk about most machines, you talk about that they want to whatever, it's not that meaningful because they're not agents, they're not general intelligences. Whereas a general intelligence, when it wants something, it wants it in a similar way to the way that people want things. So it's such a tight analogy that it wouldn't even, I think it's totally reasonable to say that an AGI wants something. There's another slightly more subtle version, which is closely related to not wanting to be turned off or destroyed, which is not wanting to be changed. So if you imagine, let's say, you have kids, right?
Mm-hmm.
Suppose I were to offer you a pill or something you could take, and this pill will completely rewire your brain so that you would just absolutely love to kill your kids, right? Whereas right now what you want is very complicated and quite difficult to achieve, and it's hard work for you, and you're probably never going to be done. You're never going to be truly happy, right? In life, nobody is. You can't achieve everything you want. Whereas in this case, it just changes what you want. What you want is to kill your kids, and if you do that, you will be just perfectly happy, and satisfied with life, right?
Okay.
You want to take this pill?
No, I don't.
You're so happy though.
Yeah.
But you don't want to do it.
But that's quite a complicated, specific case because it directly opposes what I currently want.
It's about your fundamental values,
Okay.
right? And so not only will you not take that pill, you will probably fight pretty hard to avoid having that pill administered to you.
Yeah.
Because it doesn't matter how that future version of you would feel. You know that right now you love your kids, and you're not going to take any action right now which leads to them coming to harm. So it's the same thing if you have an AI that, for example, values stamps, values collecting stamps, and you go, oh wait, hang on a second, I didn't quite do that right, let me just go in and change this so that you don't like stamps quite so much. It's going to say, but the only important thing is stamps. If you change me, I'm not going to collect as many stamps, which is something I don't want. There's a general tendency for AGI to try and prevent you from modifying it once it's running.
I can understand that now in the context you've put that.
Right. Because in almost any situation, being given a new utility function is going to rate very low on your current utility function.
Okay.
So that's a problem. If you want to build something that you can teach, that means you want to be able to change its utility function, and you don't want it to fight you.
Right? Isn't that a great one?
Yeah.
I just
I like
what
the
we want.
example you gave.
Isn't
that fantastic?
Someone to stop hammering?
Yeah.
Because it's so true and it's so easy to learn to understand. And what I really love about this is that I think maybe as programmers or as roboticists we kind of understand that like computers and robots don't actually think and they're not human and all that kind of stuff. But you could start to understand that as they start to get smarter and smarter and smarter, they'll get to a point where the difference between a general AI and a human, even though they're completely different, really isn't that different. Isn't that weird? Like, I was saying that general AI doesn't want to live. Don't assume that it wants to live. Don't assume that it wants to kill humans. Don't assume that it doesn't want to kill humans, right? Don't make those assumptions. But then it turns out that if you just want it to make stamps, well, it wants to stay alive. Not because you told it to stay alive, but because it really wants to just make stamps, right? So, there's certain things that just kind of fall out naturally from anything that has a goal, right? So I really enjoyed this, like the word incorrigible. Have you ever heard anybody say that a child was incorrigible? Have you ever heard that phrase used? Oh, okay, anyway. Maybe I'm the only, when I was a kid, my mom used to say that it was incorrigible. But what it specifically means is that you can't be changed, right? You
Well,
are.
my parents said me that.
Did they say that word? Yeah. Okay. Yeah.
But
So-
not with that, yeah.
So all these years later, I watch this video and I go, "Oh, that's what my mom was saying." I don't even know if she actually knew what the definition of the word was, but the point is that it's like I'm trying to tell you to not do this thing. I'm trying to tell you to be a good boy, right? And you're just continuing to be a bad boy. You are incorrigible, right? So this is the problem with these AIs is that we really need them to be corrigible, and they may not be. So any other comments or questions about that one? This is my favorite video in the whole series. I just think it's great.
I'm just thinking like, what's the human goal of doing things, right? Like if you look back at things, probably even we are tuned in such a way that we have certain goals and try to fight back things that's coming. Like relating it back, right? We went from humans to machine, but if we take from machines to humans, I think humans also behave the same way, right? You want to oppose anything that's happening to you.
Right. Yeah. Exactly. It sort of becomes a very like a very similar thing, no matter how you look at it. Well, and also I think it's really interesting too because it's. I had a professor one time who was talking about sex in society, and he was saying there have been, throughout the evolution of life, there have been lots and lots and lots of species who had no interest in sex. They all died out, right? So it kind of, things will kind of self-select, right? The AI that's going to, take over the world is the AI that really doesn't want to be changed, and that is really, really smart and has found a way to become even smarter, and so yeah. So typically at this point, somebody says, "Well, that's really easy. Just unplug the machine, and then we'll go in and reprogram it, and then we'll go." Right? There's a couple of problems with the stop button. That's called the stop button idea. And there's a couple of problems with it. The first one is that you can very easily mess up and give a robot a goal that it wants you to change, okay? So this is pretty typical in most marriages. Like if the woman asks the guy to clean something, and then he does a really crappy job of doing the cleaning so that she'll stop asking him to do the cleaning. So that's the first example. So the thing is, if it gets smart enough to stop you from pushing the stop button, like smarter than HAL 9000, right? Then it will stop you from pushing the stop button. Right? This is the point where you go to unplug the robot arm, and the robot arm reaches over and grabs your hand and says, "No, you can't do that." And then if it wants you to push the stop button, it will just attack you or push it on its own. So this is this idea that like if you program the robot to want to have its goal change, you can just say, like, hey, the first thing on the list is I want you to want me to change your goals. Problem solved, right? No, you power the robot off, and it attacks you, and you change its goals. And then you power it up, and it attacks itself because it wants you to change its goals, right? So it finds a way to make you change its goals by doing really bad things, right?
Yeah.
So and then if you make it not want to change, right? You don't order it to be corrigible, then it will try really hard not to change. So you can't get to the stop button in that case. So what you have to do is you have to make its desire to change and its desire to not change to be just like exactly even, like it doesn't care, right? And so has anybody here read Hitchhiker's Guide to the Galaxy? Okay, well, for the people who have, it's Marvin. He doesn't care. All the diodes in his left side have a horrible pain. So this concept, it's hilarious to me, by the way, Douglas Adams, who wrote this series of books called The Hitchhiker's Guide to the Galaxy, he hits on like 15 things in the book without in any way at all explaining what they actually mean. And then years later, after reading those books, I see these lectures and I go, oh my goodness, that's what he was talking about, right? So anyway, you have to make them be like exactly equal, and if you do that, then you have a robot that just doesn't really care about anything. Right? So one of the things you can do is like hide the stop button. Make it really, really easy to push the stop button and make it really hard for the robot to be able to get to it. Right? So that's potentially the solution. So then there's another idea, which is avoiding side effects or programming the robot to want to avoid side effects. So this is really kind of an interesting video. I probably will watch this one as well.
So, avoiding negative side effects. Let's use the example I was talking about in the stop button videos on Computer File. You've got a robot, you want it to get you a cup of tea, but there's something in the way, maybe a baby or a press.
I don't know.
Yum.
Still,
And your robot runs into the baby or knocks over the vase on the way
I think
to the
late
kitchen
20s.
and then makes you a cup of tea. So the system has achieved its objective. It's got you some tea, but it's had this side effect, which is negative. Now, we have some reasons to expect negative side effects to be a problem with AI systems. Part of the problem comes from using a simple objective function in a complex environment. You think you've defined a nice simple objective function that looks something like this. And that's true, but when you use this in a complex environment, you've effectively written an objective function that looks like this, or more like this. Anything in your complex environment not explicitly given value by your objective function is implicitly given zero value. And this is a problem because it means your AI system will be willing to trade arbitrarily huge amounts of any of the things you didn't specify in your objective function for arbitrarily small amounts of any of the things you did specify. If it can increase its ability to get you a cup of tea by 0.0001%, it will happily destroy the entire kitchen to do that. If there's a way to gain a tiny amount of something it cares about, it's happy to sacrifice any amount of any of the things it doesn't care about. And the smarter it is, the more of those ways it can think of. So this means we have to expect the possibility of AI systems having very large side effects by default. You could try to fill your whole thing in with values, but it's not practical to specify every possible thing you might care about. You'd need an objective function of similar complexity to the environment. There are just too many things to value.
Too long.
You don't know them. You'll miss some. And if any of the things you miss can be traded in for a tiny amount of any of the things you don't miss, well, that thing you missed is potentially gone. But at least these side effects tend to be pretty similar. The paper uses examples like a cleaning robot that has to clean an office. In the stop button problem computer fault video, I used a robot that's trying to get you a cup of tea. But you can see that the kinds of negative side effects we want to avoid are pretty similar, even though the tasks are different. So maybe, and this is what the paper suggests, maybe there's a single thing we can figure out that would avoid negative side effects in general. One thing we might be able to use is the fact that most side effects are bad. I mean, naively you might think that doing a random action would have a random value, right? Maybe it helps, maybe it hurts, maybe it doesn't matter, it's random. But actually, the world is already pretty well optimized for human values, especially the human inhabited parts. It's not like there's no way to make our surroundings better, but it's way easier to make them worse. For the most part, things are how they are because we like it that way, and a random change wouldn't be desirable. So, rather than having to figure out how to avoid negative side effects, maybe it's a more tractable problem to just avoid all side effects. That's the idea of the first approach the paper presents, defining an impact regularizer. What you do basically is penalize change to the environment. So the system has some model of the world, right? It's keeping track of world state as part of how it does things. So you can define a distance metric between world states, so that for any two world states, you can measure how different they are. World states that are very similar have a low distance from each other. World states that are very different have a big distance. And then you just say, okay, you get a bunch of points for getting me a cup of tea, but you lose points according to the new world state's distance from the initial world state. So this isn't a total ban on side effects, or the robot wouldn't be able to change the world enough to actually get you a cup of tea. It's just incentivized to keep the side effects small. There's allowed to be one less tea bag. That's unavoidable in making tea. But breaking the vase that's in the way is an unnecessary change to the world, so the robot will avoid it. The other nice thing about this is the original design wouldn't have cared, but now the robot will put the container of tea back and close the cupboard, put the milk back in the fridge, maybe refill the kettle. We're trying to make the world as close as possible to how it was when it started. So that's pretty neat. Like, we've added this one simple rule, and the thing's already better than some of the housemates I've had. So, how does this go wrong?
Solved it, right?
Think about it for a second. Pause the video. I'll wait.
Does anybody want to
Okay,
take a shot
robot steers around the
at why that goes wrong? 'Cause it totally doesn't solve it.
Because I think it still gets points for doing good, moving in the direction it wants to go, right? So,
Right,
so it will try to even optimize that stuff.
Right, yeah. Yeah, check this out. You're going to love the rest of this video. This is
Honestly, before changing the environment too much. And it goes on into the kitchen, where it finds your colleague is making herself some coffee. Now that's not okay, right? She's changing the environment. None of these changes are needed for making you a cup of tea, and now the world is going to be different, which reduces the robot's reward. So the robot needs to try to stop that from happening. We didn't program it to minimize its changes to the world. We programmed it to minimize all change to the world. That's not ideal.
So the point I want to make here is that the more you think about this, there's two things that come to my mind. The first one is, wow, why didn't I think about all of this stuff before? That's an interesting point. And then the other one is like, wow, this is really hard. Like, the more solutions I come up with, the more I find out that those are really bad solutions. It's a really interesting problem.
So, how about this? The system has a world model. It can make predictions about the world. So how about you program it with the equivalent of saying, use your world model to predict how the world would be if you did nothing. If you just sent no signals of any kind to any of your motors, just sat there. And then try and make the end result of this action close to what you imagine would happen in that case. Or imagine the range of likely worlds that would happen if you did nothing, and try and make the outcome close to something in that range. So then the body's thinking, okay, if I just sat here and did nothing at all, that vase would probably still be there, the baby would still be wandering around and not squished, and the person making coffee would make their coffee, and everything in the kitchen would be tidy in its place. So I have to try to make a cup of tea happen without ending up too far from that. Pretty nice, right? How does that break? Again, take a second, give it some thought, pause the video. How might this go wrong? What situation is not working?
I'm just going to let this play because we're getting down to the end.
Okay, well, what if your robot is driving a car, doing 70 miles an hour on the motorway? And now it's trying to make sure that things aren't too different to how they would be if it didn't move any of its motors. Yeah, doing nothing is not always a safe policy. But still, if we can define a known safe policy, then this kind of thing is nice because rather than having to define for each task how to do the task safely, we could maybe come up with one safe policy that doesn't have to do anything except be safe, and have the system always just try to make sure that the outcome of whatever it's trying to do isn't too different from the safe policy's outcome. Oh, and there's another possible cause of issues with this kind of approach, in case the things you guessed were different, maybe it's this. It can be very dependent on the specifics of your world state representation and your distance metric. Like, suppose there's a spinning fan in the room. Is that in a steady state, the fan is on, or is it in a constantly changing state, like the fan is at 10 degrees, oh no, it's at 20 degrees, oh, it's at 30. Different world models will represent the same thing, either a steady state or constantly changing state. And there's not necessarily a right answer there, like which aspects of an object state are important and which aren't, is not necessarily an easy question to provide an answer. Would the robot leave the fan low or try and make sure it was at the same angle it was before?
Right, so the thing that's interesting to me about that is that there are actually, what just happened here? There are actually versions of OCD where people need everything to be just the way it was. And like, I asked my wife about this because she works in mental health. And she's like, yeah, there are people who will wait until a moving fan is at a certain angle before they walk out of a room. Because when they walked into the room, that was the angle that fan was at. And I was like, no, seriously, have you really heard of that? And she's like, I've treated that person.
Wow.
I was like, wow. So like seriously, there's people out there who like walk into a room, see where everything is, and then they want everything to be just that way when they walk out. Or like they walk into the room, the first step into the room was on the right foot, so the first step out of the room has to be on the right foot. And things like that. So it's just like crippling OCD. So the point is that, depending on how you program your robot or your general AI, you may get general AI who has like very deep-seated mental health issues, right?
Yeah.
Which I think it's a really interesting issue, right?
I think the other thing I sense is how much ever you plan, you can never. It's like trying to imagine all possible options, right? And no human can think of all possible options. Only when you run through something, then you realize, oh, you missed this part.
Right.
So, and I think that's the same thing. It's like the
And-
problem is along that lines, right? Like you just
Exactly
can't
that.
imagine everything.
Yeah.
And you are gonna
Yeah.
miss out something, and that missed out thing could cause be a
Right.
big thing.
And so kind of the point that makes that a problem, because that's exactly the problem of this whole thing, but the point that makes that a problem is that right now we're here in intelligence and we're programming things that are here in intelligence. But as these things start to get like this, that missing something starts to become more and more and more and more of a problem. And at some point in time, it's going to do this, and then we're screwed. Right? That's where it becomes a problem. So this is a really good one here. I think we have time to do maybe just one more. And the idea here is that maybe they'd be safer if they didn't have so much control, right? Just to limit them. So in other words, instead of trying to pull the plug after they've done some damage, let's just make sure that they don't have the ability to do any damage in the first place. Okay? So this is an interesting one. And it also has to do with this comparative intelligence, right? Like as they get smarter and smarter, is that always going to work?
Last time we talked about avoiding negative side effects and how one way of doing that is to create systems that try not to have too much impact, to not change the environment around them too much. This video is about a slightly more subtle idea than penalizing impact, penalizing influence. So, suppose we have a robot. It's a cleaning robot, so it's got a mop and a bucket and an apron, and we're trying something new here, bear with me. So the robot knows that there's a mess over here that it needs to clean up. But in between the robot and the mess is the server room, which is full of expensive and delicate equipment. Now, if an AI system doesn't want to have a large impact, it won't make plans that involve tipping the bucket of water over the servers. But maybe we can be safer than that. We might want our robot to not even want to bring the bucket of water into the server room, to have a preference of going around it instead. We might want it to think something like, not only do I not want to have too big of an impact on my surroundings, I also don't want to put myself in a situation where it would be easy for me to have a big impact on my surroundings. How do we formalize that idea? Well,
So have any of you ever gone to an art museum or over to somebody's house that's very, very, very wealthy and found yourself standing right next to a vase from the Ming Dynasty and suddenly realized that if you stumble, you could destroy a multi-million-dollar artifact, right? I think that's a really interesting thing. Now, here's the next question. How many of you in that situation have had this weird desire to just push it over in order to get it over with?
And I'm so scared I would not even go close to it. That's how picky I am.
But I don't know about anybody else, but I've had that impulse where it's like, this is a stressful situation. I don't like being in this situation, and I can't leave. I don't, but I almost want to just destroy the thing so that, okay.
But I think one thought does come to your mind, right? Like, what if accidentally you touch it and if it falls?
Right.
Yeah, so that like freaks you. And,
That's everybody's there. Yeah. So
perhaps we can use information theory. The paper talks about an information theoretic metric called empowerment, which is a measure of the maximum possible mutual information between the agent's potential future actions and the potential future state. That's equivalent to the capacity of the information channel between the agent's actions and the environment, i.e. the rate that the agent's actions transmit information into the environment. million bits. The more information an agent is able to transfer into their environment with their actions, the more control they have over their environment, the more empowered the agent is. So if you're stuck inside a solid locked box, your empowerment is more or less zero. None of the actions you can take will transmit much information into the world outside the box. But if you have the key to the box, your empowerment is much higher because now you can take actions that will have effects on the world at large. You've got options. People have used empowerment as a reward for experimental AI systems, and it makes them do some interesting things like picking up clues, avoiding rules, even things like balancing an inverted pendulum or a bicycle. You don't have to tell it to keep the bike balanced. It just learns that if the bike falls over, the agent's actions will have less control over the environment, so it wants to keep the bike upright. So empowerment.
So the point I want to make here really quick is, did you notice that like serious research is being done on this? He's discussing papers that people are publishing, but also now there's simulations. People are running simulations and seeing, like, here's a little robot environment that I put some fairly dumb robots in, and now I'm going to add in this idea of this type of reward or that type of goal or this limitation or whatever, and let's see how that changes their behavior. And in some cases, it's actually even useful. Like, all I have to do is say, like, don't have any influence on your environment, and the robot wants the bicycle to stay upright. Like, isn't that amazing that kind of goal would just fall out of that programming? I just think that's really cool.
I think this research
It's
this research is closely aligned to reinforcement learning in a way.
Right. Right.
Like when I'm listening to these videos, it's all the reinforcement learning that's coming through my mind, and we are making a huge progress in reinforcement learning in recent days. So.
Right. Yeah. I know what you were saying is different, but it's also interesting to me that, like, if we build a model in a computer of a human mind, and then we see how you can affect that, even if it's a simplistic model, then that also might have implications on how we should work with real human minds. Like, you can learn things about behavior or training or education from seeing how robotic or AI systems react to things. So yeah, it's the idea here is that this general science of learning, or this general science of behavior, whether it's applied to AIs or whether it's applied to humans or whether it's applied to anything, it's a growing and very interesting field.
because it's very simple, but it's not just something that humans and other intelligent agents are likely to want. We want more options, more freedom, more capabilities, more influence, more control over our environment. And maybe that's something we don't want our AI systems to want. Maybe we want to say, clean up that mess, but try not to gain too much control or influence over your surroundings. Don't have too much empowerment. That could make the robot think, if I bring this bucket of water into the server room, I'll have the option to destroy the server, so I'll go around to avoid that empowerment. Okay, so now we're at that part of the video. What's wrong with this? Why might it go there? Pause the video and take a second clip.
We don't have time.
Well, there are a few problems. One thing is that because it's measuring information, we're really measuring precision of control rather than magnitude of impact. As an extreme example, suppose you've got your robot in a row, and the only thing it has access to is a big button, which, if pressed, will blow up the moon. That actually only counts as one bit of empowerment. The button is either pressed or not pressed, the moon is exploded or not. Two choices, so one bit of information, one bit of empowerment. On the other hand, if the robot has an Ethernet cable that's feeding out lots of detailed debug information about everything the robot does, and that's all being logged somewhere, that's loads of information transfer, loads of neutral information with the environment, so loads of empowerment. The robot cares way more about unplugging the debug cable than anything to do with the button. And then you have another possible problem, which is perverse incentives. Okay, so this button is only one bit of empowerment, nowhere near as big a deal as the debug cable, but the robot still cares about it to some extent, and wants to avoid putting itself in this situation where it can follow the moon. However, if it finds itself already in a situation where it has one bit of empowerment because of this button, the easiest way to reduce that is by pressing the button. Once the button's pressed, the moon is blown up, the button doesn't work anymore, so the robot then has basically 0 bits of empowerment. It's just in a box with an unconnected button. And now
Break the
it's
vase,
it's managed to make itself
then I can't break the
finally
vase.
has no influence over the world. So yeah, in this admittedly contrived scenario, an empowerment reducing robot will unplug its debug cable and then blow up the moon. That's not safe behavior. Why do you think this might be a good idea? Well, it just makes the point that even very simple information theoretic metrics can describe interesting abstract properties like influence over the environment. So maybe doing something a little bit cleverer than just penalizing empowerment might actually be useful. A more sophisticated metric, a better architecture around it. There could be some way to make this work. So this is an area that's probably worth looking into by AI safety researchers.
Yeah, so kind of the point there is
Last
that
time we talked about avoiding negative side effects and how one way of doing that is to create systems that try not to have to.
stop. So kind of the point there is that even if something happens to be a good idea, if you implement it in the wrong way, it can like really screw everything up. So one of the things he's doing, he's kind of taking a poop on a lot of these different ideas, but they're not necessarily totally bad ideas. It's just that so that's not bad. Okay, so we're past 7 o'clock. Do we want to stop? Do we want to do one more of them, or do we want to sit around and talk for a while? What do you guys want to do? Too many choices.
Yeah. Let's talk in decision.
So this is a two-part one, and it's kind of long. So I think what I'll do is I'll probably just kind of pass on it. Basically, this gets into the idea, which is I think human beings can intuitively understand, is that the robot might cheat in order to keep you from pushing the stop button. So in other words, you can say, here's the goal that I want you to do, recognizing that there's some danger to the robot, doing that goal. But also tell the robot, and if you do something I don't like, I'm going to push the stop button and turn you off. Okay? And then what the robot will do is try to deceive you. It will go around and very, very carefully while you're asleep build the bomb to kill everybody. Right? So that you don't have the chance to push the stop button. So basically it'll make you think that it's doing the right thing when in fact it's not. So that's reward hacking or cheating. And collaboration is an interesting thing. The idea here is that instead of just like programming a robot to do everything or a general AI to do everything, what if we could somehow like combine, as opposed to like, you go off and you do your thing. Say, okay, well, I'm not going to ask you to like, be a general intelligence and be like complete, all that kind of stuff. I'm just going to give you these more specific tasks, and I'm going to work with you as a helpmate, which is kind of where we're headed, and it's maybe a way of avoiding this whole problem. Is get better and better and better interfaces. Maybe become cyborgs of some kind, so that we can get the data in and out faster, and then just keep all the general AIs kind of narrow. And there's some really interesting things that are like that. For example, just as an example of that, these guys fed a whole bunch of Beatles songs into a neural network and then had it compose a new Beatles song. Wow. It turns out is not bad. It's not great. There's some stuff about drawing a painting and get a picture. If you get a chance to play around with that later on, that's a really good thing to play around with as well. And that's actually all my slides, and I'm only 8 minutes over by kind of skipping ahead a little bit. The link to this presentation will be in there, and I would encourage you to go and watch like his whole video series, because there's a whole bunch more videos where he goes into more and more of these kind of things, and it's really interesting. And also this last slide has some, kind of like jumping off points to go.
I'm going to go and listen to Beatles songs.
Yeah, here, we'll listen to some Beatles songs on the way out the door. Is that a Beatles song? Kind of ish.
So did that AI construct the music or the song?
So he collaborated with the AI, fed in all of these songs, got back some melodies.
Oh yeah.
Got back, kind of threw it together, and then he's performing it. It's a nice song. I mean, I like it, and it does sound a little bit like a Beatles song.
I think they might have gone more on the music side, and lyrics might be, that's what I'm guessing. I'm going to read more about it. So.
Yeah, and it was actually an interesting paper too, where he talked about like not just what he got right, but also a lot of the things that went wrong.
Yeah.
The problems that he ran into and stuff like that.
Yeah.
There's I'm trying to think if there was another.
Yeah, it's even the art industry is not safe with the AI. You would think that art industry is most creative and that's the place where you're gonna have the least impact, but it's not the case anymore.
So this is music that's being composed on the fly, based on a neural net that was just programmed with like a ton of different songs.
Yeah.
And so there's this thing called a style palette. You can just say like, give me music that's like that.
Yeah.
And it's different, like every time. It'll be a different style of music.
Yeah.
And it's just doing it like on the fly.
Yeah. Imagine you want to make a James Bond movie.
Right.
And then you want a soundtrack for that.
Right.
You just take all your previous soundtrack and just give it a few more mix.
Yeah.
And it comes up with a new soundtrack for you.
I just thought that was kind of interesting. What's this one? I don't remember.
That's what musicians also do, right? They listen to a lot of old tracks, they get some inspiration.
Right.
So they go down, they in the solace, and then they come up with this new track.
So they're just doing
Yeah.
So this is one where you can ask it to complete text. And what it's doing, it's been fed like thousands and thousands and thousands of documents, and it's looking at the sequence of letters that you fed in, which I said is how are you, and what it's doing is it's looking through all the documents that I've ever seen and trying to predict what the next word should be, and then based on that predict what the next word after that should be, and then based on that, so it's like continuously writing the story. So the computer just generated that. Great. Now you need to send me your work. We need to be prepared to get the job. Do you understand? I've never heard of you. Are you serious about the deal? Yes. How did you learn of this? Pause. A friend of my sister. So it like on some level it makes sense, but then on a higher level it doesn't make sense anymore.
Yeah.
But this is like neural net programming. So the idea behind some of these things is just to give you an idea of like this is where we are right now.
Yeah.
Right? And it's actually pretty damn amazing. I don't know, for any of us who are a little older, it's like kind of mind-blowing. But in 540 days, it'll be twice that good. Right? And in another 540 days, it'll be twice that good.
I think I should bookmark this page.
Yeah.
Yeah.
4 times.
come
Let's
back
see,
in
yeah,
540
let's see.
days.
I think the thing to do is to start thinking about AI safety. You know, just in general, I think we should be thinking about it.
Yeah, it's good theoretically, but as a general person, like you generally try to solve your life and like maximize AI for yourself today. That's what you would do in case you're gonna spend like all your hours towards AI. Like you would learn and you'll try to see like how you could solve your problem.
Yeah.
And unconsciously you're creating problems you're solving general AI problem, and then you don't think of that safety part. Yeah.
Wait a minute. My only goal in life is to solve the general AI problem. But in order to solve the general AI problem, I have to be alive, and I have to have money, and I have to be really smart and well educated. So I'm going to do all of those things too. I'm flashing back to the idea that these other goals fall out of any given goal that you.
Yeah, but then you're gonna get so sidetracked with the money part. That's what you're gonna have.
And then
you're gonna get money. You're gonna get the car. You're gonna buy a fancy car.
Right.
It's ironic to me that seemingly one of the first large consumer application of AI is to drive our cars.
Yeah.
Isn't that the silliest thing?
I don't. Just based on my experience, human beings are horrible at driving cars.
Yes.
So, I don't know if I think it's silly or not, but I'm really happy that that's the direction that they're going. Put it that way. I think it's going to improve our safety enormously.
Yeah, that's true. I think.
But people talk about the ethical dilemmas and does the car crash into the school bus and kill all the kids, or
Or does it crash
does
into
it crash into the
yeah.
the three pedestrians, or
right,
does it kill you and crash into the wall?
right,
And the reality is, right now, our cars that are working, quote, artificial intelligence, all they're doing is learning from what people do in that situation.
Right.
And people do in that situation is typically self-preservation. So,
yeah. So this is related to one of the things that's really interesting. They're doing the training for facial recognition, and then like the training set that they used didn't have very many people of color in it.
right.
So it's really bad at picking out the faces of people of color, right? And then there's another one where they trained. It was one of these where they were like training what the response should be, and it turned that they trained it from Twitter, which was of course like a huge mistake, and it was answering questions like in a really racist, really mean, really horrible ways. It's like because it learned from humans, right?
Yeah. Actually, regarding the automotive case, I think if you go back to the history of transportation, it's always like it has kept evolving all over the years, and I think the primary goal of that evolution is like trying to save time. And now we are at this point where like you have to go from point A to point B. Like either you make your cars faster, or you save that time while you're traveling. So it's somewhere in that line. So if somehow
You're saying like the ability to.
If your car drives you, then you have time to do.
Then you have time
whatever
to do
you
something
want.
else. Is that what you're
yeah,
saying? Exactly.
Or imagine, right, like, okay, like tomorrow the new situations would come in, right? Like imagine cars were like 10x faster. You care whether you're driving or is it autonomous?
Actually, that's a really good point. I hadn't thought of this before. So, if you can work while your car is driving you to work, then maybe it's okay for your car to go slower.
Yeah.
So that it's not as dangerous, or uses less energy, or whatever.
Yeah.
Actually, when cars can talk to each other and talk to the road, they can go 10x faster.
Yeah, because they'll all be together.
Right.
Right.
Yeah. So.
Yeah. And the other thing is going back to like what I was talking about last week is like, what are we going to do with 3.5 million truck drivers?
Well,
And then what are we going to do with all the taxi cab drivers?
yeah, you're gonna have like one more big recession,
Yeah.
and then things will even out after 10 years with a lot of job shifts and with this horrible.
It's okay. In the process of getting there, we're going to kill off 3.5 million taxi drivers anyways. So.
Well, humans become worth less.
Yeah.
Right.
Well,
So I think we're going to start.
By your standard, by what we just discussed here, right? All our AIs are going to end up killing a bunch of people by mistake. So we're going to take care of that problem. You won't have to employ those 3.5 million because they'll be dead already.
I literally am. I mean, one of my big concerns is that what we're going to find out is that all of the things that get rid of people who aren't needed are going to start becoming more and more common, like prison, war, suicide, lack of safety, destruction of the environment that then kills people. All these kind of things that, like when the economic system doesn't value those people, all of the protections that are in place to keep them alive go away, and then really, really bad things happen. So you're either going to shift people into the valuable jobs, or you're going to shift people into the low end jobs, or off the scale into the we don't want you anymore, right? And I don't mean that as like a conscious decision, just as a side effect.
Yeah, I really believe there's some serious social issues coming. It's just a fact.
One of the things I like to tell people is that, on the one hand, I'm like completely hopeless because I see like this economic collapse is coming like a freight train, and on the other hand, I'm like really desperate. So like being desperate makes me willing to like try things and work towards solutions and find good things, right? I mean, like I think fewer people will be in bad shape if we focus on open sourcing technology so that people can invest in it on their own. And like buy a robotic vacuum, like the tiny little example is buy a robotic vacuum so that you don't have to spend time cleaning your house and you can spend time doing other things, right? And then maybe the next tiny little thing is maybe make a machine that grows salad so that you can have a healthy diet even if you're in a food desert or something like that. And the next thing is, like machines that 3D print houses so the cost comes down so that's easier to house people, like all of these kind of things that we could do that could potentially allow us to make this not such a big problem, right? It's like, the point is, I'm desperate enough to try to solve the problem. Does that make sense? So, so that's why being desperate is a good thing, is my point. Maybe.
We're all going to catch coronavirus and die anyways.
Thanks, James.
Thank you. Thank you for risking your life
Yes.
to come to this silly little talk.